Good afternoon, everyone. Hope you guys are doing well. In the previous lecture, we discussed about breadth first search for graphs. In this lecture, we're going to be discussing about depth first search. Both algorithms are very simple and operates almost in same time. However, there is a subtle difference and advantages and disadvantages for both kind of algorithms. Let's talk about depth first search today. So as we have taken this graph example in the previous lecture, so we're going to be using the same graph. So you can apply the algorithms for directed or undirected graphs. The idea here is to understand the basic concepts. Okay. So remember, this graph is stored as the adjacency list, as we have seen in previous lecture. What is the adjacency list representation? Say for example, we are going from vertex A. What are the connections from the vertex A? Is B and S. Okay, same way you can fill it up other connections or the full adjacency list. Say for example, S is connected with A, S is connected with C, S is connected with G. Okay. Can fill it up all other entries in adjacency list. So that's a storage efficient structure for storing. Now, as we said that if you have, so there is a preference on storing when you want to make use of matrix representation and when you want to make use of adjacency list representation. Typically, you have to basically analyze or say how many edges you have compared to vertices and so on. For this algorithm, the approach is similar, that we want to color the vertices so that we know that these vertices are visited or not visited. Now here, this algorithm, depth first search, we can use the beautiful concept of recursion for this algorithm to work. The idea is very simple. In the breadth first search, we were expanding, our both arms. Okay, but in the depth first search, the idea is to go deeper. Let's say we went from S to C. Then we want to analyze from what is connected from C to other sites. So C to G is connected, D is connected, and let's say we want to explore further. So we went from C to D and to E until we find the end. Okay, so that's the basic idea. So we want to keep looking till we end. So it's a very simple analogy you can think of, that let's say you yourself, okay, you have two luggage in your two arms or two boxes. Okay, and in the breadth first search, what did you do? Okay, you take it out the first box and you check here, then you took it out first box, you check here for in both the hands. But in the depth first search, what you're going to do, you're going to cover only first arm first. So you went to the box 1, you didn't find, then you went to the another box, you didn't find, and then you went to the another box, and then you turn your attention when you finish this branch, then you go to the other branch. Okay, so that's the basic idea, going deeper. So as you can see here, we have some coloring that, okay, whatever vertices we have in the graph, so we initially make it white, and predecessor is nil. We don't know what is predecessor so far, and we maintain a time stamp for this algorithm. So time is nothing but what time when we visited. and it's just an integer number. Let's say we went from S to A, so that means 1. We visited at time 1. Okay, and we maintain 2 timestamps. So one is a discovery timestamp, okay, and so we can call it u dot d when the vertices is discovered, and then another timestamp is u dot f when the vertex is finished. And this is sort of important if you want to analyze some statistics to know, because we are in the recursive loop. So at what time this vertex gonna be finished. Okay. Remember, this algorithm is going, the idea here is to go deeper first, then across, then the breadth. So first go deeper. It's just a different idea than BFS, what we learned in the previous lecture. Okay. From line number 5 to 7 is just simply for then after doing the initialization step, then if the vertex color is white, means it is not explored, then we call recursively, or we call, so this DFS visit is a recursive algorithm. So we call this algorithm DFS visit, ZU. Okay. So what is DFS visit? So simply, so let's say we are starting vertex is S, and we call this algorithm on DFS. Then what we do, we increase the timestamp, time plus 1, and what is the discover time, S dot t, and what we make this color gray, means we have partially visited this vertex. And then for each v adjacent to this source vertex S, we apply recursively the same DFS visit algorithm. Okay, only if that vertex is white, means we have not explored that vertex. So that's the basic idea of this algorithm. And then rest of the idea, when you visit completely, you make it black and update the time, and then S dot f is the final time, that okay, at this time that vertex being blacked or fully visited. So let's see how algorithm works. Initially, we made all vertices white. Okay, and then since we are starting vertex is S, okay, so in the circle, okay, node, we are representing the discovered time. Okay, this is u dot d, and the slash, and this time whatever it is right now we don't know, that will be final time, that when the vertex has been fully visited or fully discovered, or whatever you may call it, or we made it black. Okay, so initially we are at S, we updated this time, we made it gray. Okay, now for each v adjacent to this S, means C, A, and G, we're going to apply the same DFS visit procedure recursively. Simple. So see here, we don't need any extra storage like we needed in breadth first search. The algorithm is working recursively. Now here the overhead would be stack size. Say for example your particular language implementation, how the compiler maintains a stack for recursive calls. So that maybe we need to think about, if say we have 1 billion nodes, and what is the maximum stack size is supported, or how much memory do we have to support that stack size. So that's sort of a concern here. Otherwise this algorithm runs beautifully. Now another thing we need to note, that here this algorithm, say for example you want to find certain thing which is associated with the node A. Now you won't visit node A until or unless you cover or all the, say for example you picked up node C to visit, so until or unless you fully visited the node C and all these its children till the very end, or all these I shouldn't say children, I should say adjacent nodes, till you don't find any unvisited node, you won't go to this node A. So that's sort of a thing here. So in those situations where in those situations DFS is works better, but in certain situations, say topographical sorting, or you want to find out the how many forests are there in that particular graph, or how many non-cyclic paths, or there are other concepts in graph theory. So in certain cases DFS is useful. Also the memory requirements. So let's say if you don't want to have you don't want to use extra memory, or you have memory constraints, you may use DFS in those situations instead of BFS. But runtime is approximately same, say V plus E in the order of but nevertheless, let's talk about further. So we have visited S, and now we have we apply this DFS visit GS. So for each V adjacent to D, if the color is white, so color this white, this white, this white, then DFS visit that vertex, and we update the predecessor V dot predecessor with the S. So for example, let's go, we take a route to visit A first, okay, in the adjacency list. So remember that we have this adjacency list where your graph is stored, okay. So let's say you decided to visit A, that's the next vertex in your adjacency list. So make its color gray, and you update its time, okay. Time is equal to time plus 1, that is 2. Then you can pictorially see as from S we went to the A. We could go to C, G, but we went to A. That was the first in our adjacency list, okay. Now we went there, we visited, then we apply the same algorithm, DFS visit GV, and then it turns out to be that whatever vertex is adjacent to this vertex A, we visit that one and update its timestamp. So from A we went to the B, update its discovered timestamp, that is number 3, and now there is no more adjacent vertex left. So we are out of this for loop at line number 4, and then we made this color be black and update its d dot f, means the final timestamp, that 4, okay. Now we are out, and then because we were in the recursive loop, so we will automatically go back to the A, update its timestamp, and then because in our adjacency list the next vertex was C, which was adjacent to S, so we went to the C, update its discovered timestamp, then same thing, recursively applying the algorithm, what is adjacent to C, let's say D and G, and we went to G, for example, okay, C to G instead of going to D, and we apply the same algorithm recursively from the G, it's connected D, okay, and now from the D it's connected F and E, and for example we went to the F, okay, and from the F it is connected E, okay, and on the way we are updating each node's discover timestamp. Now from the E there is no more adjacent vertex which is not white, okay, is we have made all gray. So it means that we have, this is the final vertex we have now visited, or this is partially visited. So we make its color black and update its final timestamp. Now obviously we go back to F. We were in a recursive loop, and then D, and then G, and then C. See how beautifully we have visited and updated the timestamp. And now we have no more adjacent vertex left from S which is not white. Okay. Either it's black or either gray, so no more white vertex left from S. So we make S black. It's fully visited. Okay. So see how beautifully we have executed this depth first search algorithm. Now let's talk about the complexity. So the very first block, or the DFS algorithm, the initialization step, it's going to take how many, in the order of V, whatever number of vertices you have in your graph, and then the lines from in the DFS visit algorithm, from say where we are recursively visiting say 5 to 7, this will take in the order of E, whatever number of edges you have. So overall complexity for this algorithm turns out to be the same as BFS, B plus E. The only difference is that as I was saying earlier, that let's say certain applications, let's say shortest path. So this turns out to, BFS turns out to giving advantage in terms of finding quickly. However, if we want to do, say, make a tree, or we want to do a topological sort, depth first search gives advantage. Another advantage for DFS is that you don't need extra memory. You don't need to maintain a queue. Okay. But then the BFS, breadth first search, you are not maintaining a recursive loop, so you're not depending upon the stack limitation. So all those factors are there. It just depends on what application it is. Both algorithms are very simple to implement. So I hope, guys, you have enjoyed this lecture on depth first search. Thank you very much for listening. Thank you for subscribing and liking videos on YouTube. Those who have not subscribed, please subscribe. We appreciate your support and feedback. Have a wonderful